Yeah, so since this is meant to be a course, I think it's good to have some problems for you to solve. And so there's some, for the first two lectures, you can find some problems here. Alright, so to make further progress, we need to review what's equivalent homology. So first, what's K-theory? So if X, so recall that X was, so we took X to be smooth, again, quasi-projective. Could be, in fact, over arbitrary field, but we will, we're mainly interested in complex numbers, but it could be arbitrary, especially if it's an algebraically closed field. So that doesn't really matter. And so, first maybe I'll remind you what an element in K-theory. So an element in K-theory, so K-theory of X, this is generated by coherent sheaves on X. So it's generated. So it's first it's an abelian group, so generated by maybe symbols F. So this is coherent sheaf, means it's a finitely generated module over functions on X. Subject to relations, subject to the basic relation. So if I have a sheaf and I have a module, I have a submodule and a quotient module, means they form an exact sequence like this. Then I declare F to be the sum of F1. So in topological K-theory, one very often starts with vector bundles instead of coherent sheaves. And looking at my notes. And for coherent sheaf on the smooth, so this is we assumed X to be smooth. This is very, very convenient. So on the smooth, any F has a finite resolution. Resolution by vector bundles. And so this is the K of X so defined is equal to the similar group for vector. You can define similar group for vector bundles. So it has different notation. Sometimes people write K like 0 of X. It's the same thing. I mean, there are many different ways to know this thing. So this means just the K-theory of vector bundles. I just. And this is great for a number of reasons. Like for example, vector bundles have Chern classes. A general coherent sheaf and some abstract variety. Not clear how to define this Chern class, but vector bundles have Chern classes. And so in particular, so then we have Chern classes, then we have a homomorphism from. So the theory of Chern classes gives us the Chern character. Which is a map from Kx to well, on the smooth manifold, it doesn't matter if homology or cohomology. Let's say cohomology, x with q coefficients. So the way this works is that f, you resolve it by vector bundles, and then this is additive over resolution. So this goes to the sum. This is graded theory. The homogeneous components are called the component of the Chern character of f. And the definition is that Chern, if we think of the Chern classes, if we think of CK as like elementary symmetric functions, in some variables x1, x2, x3, and so forth, then Chern k is 1 over k factorial. In other words, if I have a line bundle, it's all determined by a line bundle. That goes to exponential of this first term. This is defined to be additive, but it's also multiplicative. So another feature why it's great to have resolution by vector bundles is that any sheaf you can tensor with a vector bundle. So this makes the tensor product of vector bundles. Vector bundles. Makes X ring. So, and the Chern character homomorphism not only it's additive group homomorphism, in fact homomorphism of rings. So it's clear that from this formulation, it's clear that if you have tensor two line bundles, then the first term class is set, and therefore exponential is also multiple. And so Chern character is a ring homomorphism. Further, the K-theory of coherent sheaves and K-theory of vector bundles, they naturally have their factorial different ways. So if I have a map from okay, third attempt. So if I have a map from some variety x to y, then of course I can push forward and pull back sheaves, but to have it preserve this relation, I need to include higher. So if I think maybe in the language of derived functors, I have to take the higher derived functors for the push forward and the pullback. So for the push forward, that means I have to consider higher cohomology in this push forward. And there's no reason whatsoever that if I push forward something which is locally something which is a vector bundle, this will be a vector bundle. So there's just no reason for that. And so then so what you when you push forward, it's natural to push forward coherent sheaves, because at least the push forward over coherent sheaf will at least be quasi-coherent, means it's some module over functions, and if moreover this map is proper in the support of my sheaf, then this will be a coherent sheaf. And when you pull back, it's natural to pull back again the higher derived functors for the pullback. They compute various tors. And so it's natural, it's best to pull back a vector bundle. Vector bundle you can always pull back. Otherwise you have to worry about okay, the best so example, it's not, so if I take like inclusion, so for example, where's the, if my x is xy equals 0, and the map F is just the inclusion of this into the plane, then you cannot, so if I try to pull back like the structure shape of the origin, this will have infinitely many tors. And so you cannot really pull back. So, okay. I apologize, this is wrong. So if I take like if I pull back the origin, right, so this I said is incorrect. For example, this would be if I'll take the inclusion, inclusion of the origin, x may be the origin, and I include this into the coordinate cross, and I try to pull back itself, then it will have infinitely many tors. So anyway, somehow I didn't mean to talk about this example. So, and the fact that we all want a smooth manifold means this operation, both push forwards and pullback are well, push forwards well defined as long as some properties is satisfied. Right. So now this is so now let G be a group, an algebraic group acting on X. And so then we would like to bring this group action somehow into the game. So have a homology theory that reflects this action. Then the first definition, so what it means for a group to act on a coherent sheaf. So this is, so for example, if I have a vector bundle, so if my X have a vector bundle, then to maybe I have some point X, and it's taken to another point Gx by the action of G, then to act on the vector bundle is the same as to just act on the total space of the vector bundle by transformation that are linear in the fibers. So if I have some vector V here, this goes to vector G. This should be an action like that. If you think about what this means, it's this, you can make the following definition for a general coherent sheaf. So G's F coherent sheaf is G equivariant if we have fixed isomorphism between F and the pullback of F under the action of G. And this isomorphism is a part of data. Like for example, I can, if I have any character, so it can be traced. This is part of data. Part of data. G can twist. Okay. this is analogous to the fact that if I have an action on the vector bundle, I can always tensor this vector bundle with the character of my group. It'll get a different action. And more generally, say if I have a trivial vector bundle, I can make many ways. So if I have a trivial vector bundle with space in which group X trivial, I have many ways to make it equivariant. Take any representation of my group G. And then this is the same. So you define the K group as above. This is again, it's true that everything can be dissolved by vector bundles, and this map is also. Oh, so we'll get to that map in a second. Basic. So somehow basic theorem proves it from the beginning. So basic theorem is that if G is, we only be interested in reductive groups. I mean, let's assume it from the beginning. If G acts on a normal right X, and L is a bundle, L is a line bundle, then there exists N such that G acts on L to the power N. And somehow to get a feeling for why it's important to assume normality is that, for example, if I take nodal plane cubic, famous example, so this is the group of smooth points of that is, so you can think of this, if I take out the node, then this is the same, or if I keep the node, this is the same as if I take P1 and glue 2 points with itself. Means the group of non-singular points. This is C star. And then it acts on itself by the usual group law on the cubic that acts on itself. And there is no bundle of non-zero degree that is preserved by this action. There are many ways to do it, like to see it. For example, if I think of Picard variety, so Picard variety of this group is again C star. And then this is C star acts on this Picard by the character. So if I have a variable Z, then the Picard degree, so it acts on pic D of this unfortunate non-normal X. So this is isomorphic to star itself, and so this acts by Z to the D. And so for every bundle of non-zero degree, this is nothing. There's no fixed points there. But also it's so this is one thing. And then why I have to take powers? Well, because for example, if I take P1 and I take the very basic line bundle O of 1 on this, then the group of automorphisms of P1, which is PSL2, well, it doesn't act on O of 1, because the global section of O of 1 is two-dimensional space, and there is no two-dimensional non-trivial representation of this group. So however, on O of 2 it acts. It's best but in fact somehow, since if we don't want to worry about X, it's best to assume. So for our case of X is smooth quadratic projective, will be guaranteed since we have an ample line bundle on some power of that, the group will act. So this will be, it's best to assume that G acts on an ample line bundle. Or equivalently, so if an ample line bundle gives me an embedding in projective space, means equivalently X is equivalently embedded in the projectivization of a linear representation. For us, it will be given, but it's best if you want to work with covariant K-theory of singularities, we must make this assumption. This is satisfied in those cases, but cannot be true here, because here, you see what happens is that if I have a projective space of a linear representation, it can never be the case that a torus orbit comes back to itself, just because it's not true for projective space itself. If I have a torus, if multiplicative group acts on the projective space of itself, it can only take one fixed point, send it to another fixed point. It can never come back to itself. So this is impossible for a situation like this. Keep losing the. I need a bookmark. Right. And so let's compute a basic. Let's compute the since we had some discussion what is the homology of projective space. Let's compute. So GLM acts on projective space, projective space, so maybe this may be my group. And let's compute the G covariant K theory. So this will be my X of projective space. So this is a good exercise to do. And so what are the coherent shifts? Coherent shifts on my projective space. Well, classically, coherent shift on projective space, these are just the same as so coordinates on projective space is this homogeneous coordinate ring, and you're interested in graded modules over that homogeneous coordinate ring. But modulus are, so it means you have modulo those of most of finite length. So you take, in other words, you take C star. There's C star equivalent means this graded. So it means if this P, maybe let's see, let this P be a previsualization of some vector space P. So you take C star equivalent shifts on your V. And you mod out by those of finite length, or those supported at the origin. And so the K theory is that in K theory we need to take the so K theory of in here there's up to so these are so there's so these are graded modules with respect to this C star. It means this means well, they'll drink get a drink. Basic object in here are the you just take polynomials here, means take symmetric take like the structure shift, so it's O of V, which is just the symmetric algebra of the dual of V. But what you can do is you can shift its gradient or shift the equivariant structure. So maybe you can shift it plus shifts, meaning this you have O of V. I'll write it here. So O of V shifted by some number m. This is graded by this s. So the ith graded component is s plus m plus I of v do. So this descends to the structure shift on my p, and this becomes the of. This corresponds to O of m here. And so this is, and what we need to do is we need to, among all these different shifts, we need to kill this origin. And how this is done is the origin, the structure. So maybe let's first do it in two variables. It would be easier. So then we have the structure shift of the origin. This suggests, so we have polynomials in two variables. So polynomials in x1 and x2, and the kernel of this map is just kills x1 and x2. So the kernel of that map is spanned by polynomials by x1, there is a map multiplication C x1, x2. Maybe I'll just should denote this ring. Anyway, so there's multiplication by x2, and there's a multiplication by x1. And to have the degrees right, so for this to preserve grading, I have to shift the degrees here by -1. Then it becomes a graded map. And then the kernel of this map is generated obviously by this map. Here I can take x2 and here x1. And then to have this graded, I have to put -2 here. So this is the resolution of the structure shift of the origin in two variables, because and in general, the general answer. So here is the Kazul complex. Namely, I take the structure shift of the origin. Here goes all functions, and the kernel of that, the best way to think about this, that this is all functions so the generators here, x1, x2, and so forth, they're just elements in V-dual. And then I shift it by -1. And then the next term is the second exterior power of V-dual, and I shift this by -2 here. And the differential in this complex is the Kazul differential. Namely, I take summation. What do I take? Right, I take this summation xi tensor d by dxi. So this is resolution. This is the resolution of structure shape at the origin. This is exactly what goes to 0 when we take this quotient. So it means on projective space I get. So this was on V, and now on the projective space. This is. This term goes away, and I get just the exact sequence of so structure shift of -1 of -2 and so forth. So if I denote by x or some variable, some such variable, so what did I do in my notes? Let's call it. Everything is denoted x. Maybe it's not so good. Maybe I denote by s. I denote O1 on V. Then that means this satisfies relation that summation over I -1 to the I s to the -I, and then I exterior power of the interval, this is equal to 0. This is, this is a relation. This is a relation that goes from I equal to 0 to dimension E, and this is a relation that this guy satisfies in K theory. And the better way to write it is that, so we always write expressions in K theory as functions on the the current represent. So think of this. These are representations. Maybe better. Tensor here doesn't matter. These are representations of G, i.e. they're any element in K theory of any space you can tensor by representation of a group. So these are in the basic, the ring of representation of my group. It's the ground ring for K theory. Everything is a module over this, and this is the way this relation written. But usually we write representation by writing characters, right? Replaced by their characters. Meaning, representation ring of G is the same as the ring of all possible characters, and all possible characters are just Weil group invariant elements on a maximal torus in G. So this is, so we can choose a maximal torus, maybe call it A here, and this is a set of A1 through AN. And then this relation becomes the relation this relation becomes the relation. What's the character? The character of the ith exterior power of V do. This is the ith elementary symmetric function of the variables AI inverse. A1 inverse. A and inverse. The definition of elementary symmetric function is such that this relation, so a relation becomes product of 1 minus S I inverse AI, sorry, S inverse I goes from 1 to n, and this is 0. And because if I expand this out, I'm exactly going to get elementary symmetric functions. And so this is, while it's usually when we talk about like a homology of some variety, we don't try to, we think of this as a ring, some important ring, but don't try to picture its spectrum of that ring. But in this case, this ring is really begs to be drawn the spectrum of that ring. So in general, everything, like I said, everything is every element in K theory of any of J and K theory is this is a module over characters on G. So in particular, it's a module. If we restrict character maximal torus, this is a module over polynomials on the maximal torus. And so this is I can therefore the spectrum of this will be some variety over the maximal torus. So I have some direction. Let me just draw A. This is really the maximal torus. So this is the sum. So what I'm going to draw is now the spectrum in the sense of algebraic geometry. So this being just variety defined by this equation. So the spectrum of K theory of G of P n minus 1. It has some direction which is just the maximal torus in your group, or maybe better to say the quotient by the or. You can pull back to here, or you can take the module level L group. It's usually easier. So with a symmetric polynomial, it's easier to write it in a regional variable than to write it in invariant things. So this is, you see, this is here, much simpler expression. So, and then we have another coordinate, which is the coordinate s. And so there's inverse here. And this is just the union. So there's there's like 0.1 here and a 0.1 there. They're both. This S is again corresponds to the reversible element in my K theory. So it's again like a multiplicative group. And so then we have just a union of this. I'll draw them as if they're powers of one variable, and they're really more like. So this means the variable S is A inverse. So it's a union of in a product of in a product of multiplicative group in some torus. This is a union of subtor. So if you take the logs, or you take so this is multiplicative group, you can take like exponential to go here, and then you're gonna get the in logarithmic coordinate, so log s. And then we get log AI. Zero. This will be just really a union of linear subspace. multiplicative equation become linear equation. Take logs. And this is if you and this is really the old Chern character map. This taking the Chern character map is really what it does. It takes like logarithmic chart of this variety. Makes the linear thing. And so there's some abstract definition of what a covariant cohomology is, but for our purposes, I think it's easier just to, so since all varieties we ever going to consider, their covariant cohomology is generated by K-theory. So there's some, I explained what the covariant K-theory is, and then there's a corresponding cohomology theory that this is the spectrum. So this is the log of the variable. This is really the Lie algebra of your maximal torus. And this is, there's a corresponding variety over the Lie algebra of the maximal torus, which is kind of like additive version of the spectrum K-theory. And so this is the spec of G covariant cohomology of my variety. There's some definition with it. I think also been explained in some different lectures. And so since this is, you see, this is if some algebraic variety is a union of some components, there must be some reason for that. And the reason for that is right. And then one thing I forgot somehow I want to point out at the very beginning is that the ordinary K-theory or ordinary cohomology, so non-occurrent. We'll come back to this later. Non-occurrent K-theory is the fiber of that over A equals 1. Or easier with cohomology over the fiber over A equals 1, you're going to get the equation 1 minus s to the power n equals 0, which is a true equation in here. But here, so this is the log of this is the hyperplane class, the first term class, the first term class of S, and here becomes the equation h to the n equals 0. Which is it. So this, in other words, you have n different lines, they come at n different slopes, and when if they union, if you take the fiber at here, you're gonna get the correct expression. So maybe jumping ahead a little bit, this is all that happens in K-theory. Sometimes doesn't happen in cohomology. Cohomology is it's a more delicate theory because cohomology could be odd cohomology and stuff, so that can spot. But in K-theory, it always happens. We'll come back to that. Anyway, this is visibly so this is a union of spec of KPN minus 1, the union of n components and what this components correspond to. These components, they have a beautiful geometric explanation. The components are in bijection with the fixed point. Of A on Pn minus 1. So if my torus A1 through An, its fixed points are just the ones that have the homogeneous coordinates or vanishing except 1. This comes on the right. And why? What does it mean that if I take the if I take this what does it mean that if corresponding to a component I have a particular branch of this variety? It's because if I take my O of 1, and if I take my O of 1, this is my covariant bundle, and I compute and I restrict it to pi, this becomes a representation. Of A, and namely a representation with character AI inverse. Because well, O of 1, what is it? This is the line. This is the dual of the line itself. So if I take the line that goes through this point, or the line through maybe line CPI. If I take the line itself, of course, this is a representation. If I have a fixed point in projective space, then my torus acts on the corresponding line. This acts with the character AI, because this is how diagonal matrix acts. That means on the dual line, it acts with the A inverse. Maybe the most important thing in representation theory is to tell a representation from its dual. This is especially important in algebraic geometry, that since representation and dual representation, they have similar properties, but a bundle and a dual bundle can have very, very different properties. Anyway, so the fact that I have this is a union of components have to do with this having some fixed point. And so what is this is a very general theorem to this effect that says that in fact the fiber over any A is the K-theory of the corresponding fixed set. So this picture is not, there's not enough dimension to fully illustrate this, because it illustrates only two situations where A is trivial, in which case you get the whole fixed fixed set, or A has different eigenvalues. But it's also true that if you consider, we can take A of the form which has some eigenvalues, the same some eigenvalues different, so maybe call it, I don't know, like 1, 2, 2, something like that. And the fixed point there would be a whole P2. And what will happen in this picture is that the two of this branch will come together, and so I'll have the fixed bit or union. So there are two fixed. The first line is fixed. So if I have something with repeated eigenvalues, then I get that. So if I have something with any linear subspace fixed under a matrix, has to be spanned by eigenvectors. So I can get either P1. So can I get the first coordinate, so P1, and then or in the other two coordinates, so P0. I apologize. So it's a point, and then I take P1, which corresponds to the two other coordinates. And then in this picture there, I have I have two of my branches will come together. So I have three branches. Two of them will come together, and one will stay apart. And so then the K-theory of that set looks like a point and a double point, which is correct. And the main tools to seeing this is a very general theorem. It says so. This is called localization theorem. Has a long history. It starts with maybe a T in both, but in the form I'm going to say straight now, it goes back to Thomason. It says that for any x whatsoever, for any case at all, for any x at all, doesn't have to be smooth or anything. The map. So you can consider the K-theory of the fixed locus. So A is a torus. A is a torus. And X is arbitrary. You can consider the map, the inclusion of the fixed locus inside the whole space. So maybe they have the same. So of course the A covariant theory of a space in which A doesn't act, this is the same as just ordinary sheaf tensor representations of A. So this is a map. Has a torsion cokernel, the cokernel of it. Has maybe I write the cokernel. Map is annihilated by expression 1 minus a mu, where this is non-trivial character. In other words, this is a torsion under my rec. So this is it's not this map may not be surjective, but its cokernel is torsion. And so let's see what this says in this example. So if I take an inclusion, so e.g. in our example, if I take the inclusion of a point, so I take the push forward of the structure sheaf of the ith fixed point, what would that be? Well, this is going back to the computation on the pre-quotient. This is inclusion of a line in the vector space. The structure sheaf of a line in the vector space is resolved in the exactly same way as a structure sheaf of, except you don't use the coordinate in that line. Right? So this would be, in this expression, it's a product, so this will be a product over all j not equal to I of 1 minus Si times aj. So it's like a Lagrange interpolation. It really is like Lagrange. This is from this. This is just a Kazul complex in all variables except the variables in that line. So this is, but the from point of view, from point of view of the scheme, this is like Lagrange interpolation polynomial. It's the polynomial. It's the smallest polynomial. So now, so we have a union. I have my union of subtori. It's the smallest possible polynomial that's equals 0 on all components but 1. And so it's clear. So this is the map. So in other words, I'm looking for. I'm producing. This is the map that. What's this map? Is you take. If you take these polynomials, you can then multiply by arbitrary polynomials in the A, and this will be an element in here. This will be like a sum of the session Lagrange interpolation. And it's clear you can get any function except there'll be some condition away from the origin. You can get anything you want. And just by all Lagrange interpolation. By the all Lagrange interpolation, if you're allowed to divide by all Lagrange interpolation, there's some denominators. If you allow yourself these denominators, then you can want any function you want. So it means away from this, not away from the origin, away from the hyperplane. So away from 1 minus. Away from this thing vanishes means, so I have, well, I write it like this, AI over AJ. When this thing is non-vanishing, we can get any function. That is to say that this map, the co-kernel of this map, the function we cannot be gotten, is killed by the such expression. So there's more systematic way to think about this. Is suppose now there's a more systematic way to think about this computation. Is suppose I look now. Suppose so this theorem of Thomason is true in some kind of staggering generality. I forgot what's the assumption on the field. I don't know. I've assumed the field is algebraically closed. So there's some issues with some. The K-theory gets more interesting if there's some Galois action, but I forgot what the right thing is there. But if I have a torus with algebraically closed field, that can be like arbitrary variety. Yeah, arbitrary scheme, in fact, so somehow it can be anything. From the K-theory perspective, there's no difference between a scheme and a variety, because you can always take any sheaf and filter it by the powers of nilpotent, and so that will be the corresponding quotients will be then sheaves on the reduced variety. So there's no difference between reduced variety and a scheme. But more is true. So somehow, if in addition X is smooth, then the fixed locus is also smooth. And we can also consider the pullback. And the pullback is defined. Well, for us, if X is smooth, the pullback is already defined, but it's we can have a different opposite map. Pullback. And so what is then, what will be then if I take a sheaf and I will consider the pullback of its push forward? Sorry, not equal, but I have a sheaf. So I have a sheaf F. So here I have a sheaf F. Now we're going to see the Lagrange interpolation again. And so then I take the, if I push it forward and I pull it back, what's it going to be? So I push it forward, well, I push it forward. This is, there's nothing to it. It's a map there's no hierarchy homology there. It's a map whose fibers are points or empty. So when I pull it back, I have to pull back a sheaf. We need to resolve it by vector bundles, or somehow compute the torus in some way. And so, for example, resolve by vector bundles. And that resolution by vector bundles, since my variety is smooth, that is going to locally look like again like a Kazul resolution, because you're really resolving zero in the normal bundle to your variety. So this would be what you're going to get F. This tensor the Kazul complex. Now for the normal bundle to the fixed log to the whole variety. And so from the point of view, so in other words, you get the alternating sum of exterior powers of the dual to this normal bundle. And so now if you have this map having a kernel which is torsion, what we can do is that somehow by abstracting now I have a sheaf G here. Then what I can write it like this. So I can say that what's it going to be? G will be the push forward of the pullback so if I apply, in other words, if I apply this pullback to, so I know that G is a push forward of some sheaf F plus torsion. To find what that sheaf is, I can pull back. And so then I'm going to get the expression that the G is the push forward of its pullback divided by, so the way one writes this exterior algebra, the way one writes it in formals, one writes as a product. I mean, the way I write it. Some people write it differently, but I personally prefer this expression. I think this expression is much more compact and much more somehow computer-oriented than this sort of expression. So I'll write that this is a product of 1 minus W inverse, where these are the weights. These are the weights in the normal bundle. And so here you put this product of 1 minus W inverse, are the weights of the normal bundle, so plus torsion. Or they'll say mod torsion. This is a remarkable formula. This is remarkable. This is again, this is for the case at hand that will reduce the Lagrange interpolation. It will be really a Lagrange interpolation, which is saying, if I have a sheaf, there will be the denominator, it will be the denominator, the Lagrange interpolation will be really exactly that. But the way it's used all the time is that if I want to further push it forward, now, but if I have some different map from X, like for example, if I want to have like a map to a point, for example, in the end, in K theory, we always want, at the very end, we want like a number or a representation of a group. Means we want some moduli space and stuff, and then we push it forward to a point. So, but in general, suppose I have some map pi, and I'm interested in pushing forward under this. Well, I can apply it to here, and then that means it's enough to push forward since the push forwards compose, in the composition of push forward is the push forward under the. So it's enough to integrate over the fixed locus. This is how it's used. If you want to compute like the Euler critical of a sheaf, then modular. What does it mean mod torsion? Mod torsion means I compute modular expression annihilated by these denominators. Most of the time I don't care about expression annihilated by these denominators. So a typical expression annihilated by these denominators is the difference between like anyway, you can most of the time there's no this what's a typical expression annihilated by y minus w? It's like summation of world w to all possible powers. This is annihilated by y minus w, and the way you can see it is that this you can write as it's a difference between two expressions of the same rational function. You can write it as 1 minus w minus 1 minus w, expanded in different ways. And so this will be, okay, it will be annihilated by y minus w. But most of the time we don't care about this. And so if we compute characters, for example, if I have like a finite dimensional representation of a group, its character is a polynomial. It has no terms like this. Somehow polynomials have no torsion. So. Anyway, so this tells you that if I restrict to the locus where right, and I forgot to say that this is the here in this formulation you get if your variety is smooth. In fact, you know exactly which characters you need to invert. Namely, you need to invert the non-trivial characters that appear in the normal bundle to the fixed locus, and this, of course, if X is smooth. If X is smooth, then you in fact know exactly what you have to invert. Maybe since I'm already really over time, but I'll still maybe explain one. This is kind of a very nice thing. Is that how do you see? I suppose I have in the simplest possible. We suppose of one dimension. So I claim that if I look at the fiber over let's say suppose A is just multiplicative group and acts an element in here some just little a and acts on some right x. Then my current K theory of that is some variety over branches over that. This is A equals 1, and this is general A. And I'd like to say that the fiber over A equals 1 is really K-theory of X. Meaning I have the following exact sequence. I claim there is the following exact sequence. I take A covariant K-theory of X. Here I multiply by 1 minus A. Here I have, so this is X. And here I K just X itself. Claim there is this exact sequence. And how do I see this geometrically? I can see it like this. So I can have consider X cross A1, which in this case, since I have just X, consider X cross C. So this will be, you can think of this as A covariant theory of X cross C, where this is the defining representation. This is the defining representation of my A. A is a C star, it acts, so this acts on C. And then any sheaf I can restrict to an open locus. I can restrict it to this cross C star. And the general theorem is that any sheaf on the open can be always extended to a sheaf on the, it's a basic theorem. Coherent sheaf is that if I have a coherent sheaf on an open set, I can always extend it to some coherent sheaf on the whole thing. And so this thing is surjective. And the kernel of this are the sheaves that support it at the origin. So this is, I'll write it, K theory of X. So by my writing cross, nobody, this is a product. And then across the origin. This, by this localization theorem, this is this inclusion of a smooth submanifold into ambient manifold. So this map here, if I make this isomorphism by pullback, meaning I have a sheaf here, I pull it back here, so this is isomorphism. Then this map, well, this is just the same variety. So this map by this localization theorem really is multiplication by y minus A. And then you can do as an exercise check that this is also exact. And this is really nice because something like this is generally not true in a Korean homology. In a Korean homology, there is some notion of when is some important notion of formal variety for which this is true. But in general, it's not true. And so the Korean K theory is just a nicer numerative theory. You want to compute well, I don't know. Korean homology is also a very nice theory, but the Korean K theory in some ways, in many ways, it's nicer. Yeah. So, but we're not going to do the curve counting in K theory because it's just too technically demanding. You don't want to. There's some. It's a nice in theory. It's more technically demanding, but in principle you could do it, and it just gives you nicer results. But now we go back to our curve counting. Oh right, I forgot to say here. Sorry, I apologize. Here you have an action. So here you have an action on X cross the group itself. So if I have a basic statement in the current K theory, so if I have X and I cross it with the group itself, and I consider G covariant sheaves on this, well, any such sheaf can be obtained from it's spanned by trivial sheaves on X pulled back here. Somehow I have a free action that's the same as if I have across some free action, then it's the same as I take the K-theory of the quotient. So this thing is. Right, also maybe I should point to this, is that here, since the K-theory of, or homology of projective space is generated by divisor, and its K-theory is generated by a line bundle, in general it will be generated not by a, like for Grassmannian, it's generated not by a line bundle, but rather by a vector bundle. And so here, so maybe I'll use this picture here. So here S should be, is really, again, if I have a vector bundle, there's not one S. You should think of, again, the way to think about a vector bundle is, again, is different tensor functors you can take of a vector bundle. This is like symmetric polynomials in some set of variables. So here you would have a bunch of churn roots, maybe I'll write in J. These are, kind of like a churn roots of a bundle. So what would be this picture like for Grassmannian? For Grassmannian, you have a tautological bundle. Maybe I'll draw this picture for Grassmannian. For Grassmannian, so Grassmannian Kn, then you have coordinates S1 through Sk, and you should really mod out by Sk, but because you think of tensor functors of a vector bundle as symmetric polynomials in so many variables, but it's easier to write formulas before you take the quotient, and then you have this coordinates A's, A1 through AN, and then this is also mod out by you should really take the quotient by the Weil group, but again it's easier to write the formulas in non-symmetrized version. And so then what is this if I have fixed points? So if I have a fixed point, that means I have a torus fixed point on the Grassmannian. So this is a fixed point. I take Grassmannian Kn, and I said to take the first point, then these are the same as subspaces. I'll write coordinate subspaces. That is to say, there's a set of, we take like a span of some set of coordinate vectors. I, where I belongs to some subset I, where I is a k-element set. This is a k-element subset of 1 to n. And then if I take the, say, tautological bundle or the dual tautological bundle, let's take to keep with this notation, let's take the dual tautological bundle. Then I get a copy of my torus here, where I assign S1 to be AI1. Maybe I'll write this I the subset, so it has some elements S1 through Sk, maybe not S, I1, let's call it I1 through Ik, and then I equate S1 I1, S2 I2, and so forth, because they're dual. And so this is up to permutation here and there. So this would be the. Now, right, maybe it's actually so one advantage is it's obvious that the covariant in the covariant cohomology it's the additive version of the same thing. It's obvious that this is much nicer object than the cohomology or non-equivalent cohomology. Just explicitly gives you as well some arrangement of linear subspaces, modular subgroup, but it's basically arrangement of linear subspace. And I think it's somehow much nicer, but also on a technical level. And if I'm interested in the, like if I look at the, so for example, if I look at the first Chern class of the tautological bundle, we call it V, and if I restrict it, so the first Chern class is, on the right, an additive variables here, and I restrict it to this I subspace, well, it'll be summation over I in I. The first Chern class is in additive so it's like a sum. So first Chern class, if you take the sum of Chern roots, so it's you take the additive version of them and you sum them up. So you take AI. And so this says that the operator, so if I take an operator of cup product by this guy, this is something I didn't discuss again. So if I take, we should have discussed, but I forgot. So if I take an operator of a cup product by this element here, well, this would be its eigenvalue. Right? It's clear if this, so if I have a, how to say, if I have multiplication, if I have a multiplication by a function, then the eigenvectors are the delta functions, and so the delta functions here corresponds to corresponds to this Lagrange interpolation, so it corresponds to fixed point. And so this is it. This is much first of all, this is much nicer than, again, if I have ordinary cohomology, every operator other than one is nilpotent. In ordinary K theory, every operator is unipotent, or rather, every line bundle is unipotent. It doesn't have very interesting eigenvalues. But here it has, first of all, it has eigenvalues, interesting ones. And second, these eigenvalues are distinct. Not only they're interesting, they're in fact distinct. It means that up to some, up to some localization, the ordinary cohomology of Grassmann is not generated by divisor, but the equivalent one is generated up to localization because you have an operator of distinct eigenvalues, you can get any vector whatsoever in the space from applying the operator. Clear? And so then this is this means that the quantum cohomology, which is a deformation, if you take a equivalent quantum cohomology, which is a deformation of this, has to be at least, again, will be generated by one operator. It's enough to know one operator there. If we have a ring generated by one element, and it's a deformation also generated by one element. so now the chronology. So if I have now going back to, we were looking at the spaces like M03 bar of X. So anything that acts on X acts on here. It's the automorphism group. X acts there. Okay. And the way deformation theory of a curve is obviously written in a ways that don't break any symmetries, right? Because the deformation theory comes from, like a homology of the normal bundle. So the deformation theory and the things you get from this, namely the virtual structure shift or the virtual fundamental cycle, are automorphism of X equivariant. And so everything, all counts. We're not going to do K here just because there's not enough time for this. But that's a good thing to do in principle. Like the cycles, we remember this is defined using some correspondences. These correspondences are fully equivalent. So this is all. And this equivalence is the full flavor of the theory starts to develop. And using this equivariance, I'm somehow terribly behind time. So I think it's okay. It's better to explain something than to. I think it's better to explain one thing than jump over many things. So this, we were talking about Grassmannian of again. And in fact, we will let go of this. This is a very nice variety, but we will let go of that. And we will instead consider the, so not going to, from now on, I will write X to denote the cotangent bundle of the Grassmannian. So this is, in some sense, it's much nicer. And I'll try to explain why. And so this is acted upon now. Now previously we had GLN action, but now it's acted upon by GLN in another group, which it just scales the cotangent direction. So maybe I'll write it C star H bar, where H bar scales. It's a variable that scales this with weight. Conventional H bar inverse. So that then this is a bad convention. It should have been H bar, but it's anyway. This bad convention is too late for me to change it now, I think, because the reason it was called H bar is because this is holomorphic symplectic variety, and then if you scale the cotangent direction with a certain weight, then the holomorphic symplectic form scales with the opposite of that weight. So H bar becomes the weight of the symplectic form. But in fact, it's better if you like a physics notation. H bar appears in the commutator of 2, and this is really not the weight of symplectic form; it's the weight of the Poisson form, which is the opposite. Should be. I mean, if you think of the definition of H bar as the coordinate momentum, the commutator there is H bar. So it's the weight has H bar in it. So the weight is it's better called H bar, the weight of the Poisson tensor, which doesn't matter. Anyway, this is a convention. And so we will look at this variety instead. So since since the cotangent bundle, it's obviously the first joint class of X is just 0. And so then the virtual dimension, if you remember the formula, that has the dimension of virtual dimension of M0 of 3 bar X, some degree D. Of course, by the ordinary cohomology and homology of this variety is just the same, because one is a bundle of another. But the quantum thing is different, because quantum cohomology that feels normal bundle to a curve, and so in particular depends on like first joint class. So this is some degree D. So the general formula was the dimension of X plus C1 of X dot D, and so this term goes away. So this makes the virtual all this moduli space have the same virtual dimension. And in fact, if I just say it like this, if I forget about the group equivariance, then the curve counting problem in X will be really easy, because all counts of non-zero degree are just 0. So without equivariance, without H bar equivariance, all counts of degree not equal to 0 are equal to 0. For very simple reasons. So one reason is that if like for example, X can be deformed. All the curve counts, they're set up so that they're deformation invariant. And X can be deformed to a variety which is affine. There's no curve at all. Algebraic curves at all. So this is since I'm running short of time, I'm not going to explain how this works, but you can try it. And if you have never seen this before, if you've seen the general theory of Nakajima varieties, you can think about what you've learned about general theory of Nakajima varieties. If you've never seen this before, try T star P1. And T star P1 can be deformed to an affine conic. You can just write this deformation. Or maybe say differently, for cotangent bundle, there's also notion of what's called twisted cotangent bundle. Where you and then the twisted cotangent bundle for T-star Grassmannian, they're a fine variety. Anyway, but for the reasons we somehow the local reasons that they are count is trivial, is because if I have if I have a curve in X, I'll just write it. I feel better when I have a talk about curve. I have a picture of a curve. Then or maybe a map. So this is a map from some curve. Yeah. Then the abstractions here for this map, that at this moduli points, this is going to be like H1 of the pullback of the tangent bundle of X. Now, this is, since X is symplectic, this is the same as H1 of the pullback, the cotangent bundle to X. Since I have a curve mapping to X, then the cotangent bundle of X maps to the cotangent bundle to the curve. Map, so maybe some curve C, and there's X, and this is on the curve, right? So if I have a map of manifolds one way, I have map of cotangent bundle the other way. And so then this would be, this therefore will map, and in fact, to H1 of the cotangent bundle, the curve itself. But this is somehow, if I have a top cohomology of the cotangent bundle, this is famously a canonically trivial thing. So this is somehow very, very canonical. Trivial thing. And so, this means in my abstraction space, which is this is the equations I'm going to impose, and upon my equations, I impose the equation like 1 equals 0. This type of equation. Like I impose among my equation, I have an equation, the first term class of a trivial bundle. And so this my cycle will vanish. And so, but however, equivalently, the day is saved because in the litification, if I have a scaling of symplectic form by a character, then of course this is using symplectic form. If a character scales the symplectic form, that means in this isomorphism, you're not going to the cotangent bundle, but rather the cotangent bundle twisted by that character h bar. And so that character is going to be here. It's going to be here. And so that says that while the first term class of a trivial bundle which has non-equivalent weight, that's okay. Means that is that way. And so then, in fact, that says that the virtual class we impose, there's an equation which just has weight h bar. So this means maybe h bar, and then times something which is called reduced virtual class. Now we'll combine so this will be therefore this will have virtual dimension 1 bigger. Because this is equation, so it's a virtual dimension 1 more. Now comes now will come a kind of a crucial dimension count. So this is the here in this picture. What we said, we decided that the first term class of tautological bundle generates up to localization generates classical cohomology, and so. If I want to do quantum ring, this will be again generated by this one same element. So it's enough to consider. So enough to consider quantum product by a divisor. So maybe it's a divisor. So H upper Q of X, Hg, first term class of. Now, when we compute, the curve, that's we're interested in the correspondence. 3 points lie on a curve. And so there's 3 points in X, P1, P2, P3 lie on some curves of degree D. This is a picture of my correspondence. And now, one of these points is now constrained to line on divisor. So but divisor will hit a curve in just finitely many points, namely depending on the degree of the curve D. So there's finitely many choices. So what does it mean, quantum multiplication by divisors? So I take this correspondence, and I now constrain at this point line on divisor. But this means that there's finitely many places in which my curve is going to hit that divisor. And so this correspondence here is really equal. So this is, I have to pair, so there's a divisor lambda. I pair lambda with D. This tells me how many, in this picture will be 3. So there's 3 choices of my point P2. And then that point P2 I can just forget. So right? In other words, the operator of multiplication, this is the operator of multiplication by lambda in degree D. This is, so to speak, the z to the D coefficients in here is equal to this. This is viewed as the corresponds an operator from homology of X to homology of X. This now comes from 2-pointed curves. So the virtual dimension. So what is the so this thing comes from the virtual class of 0.2x d. All right, reduced for this reduced part. Sorry, not reduced first. But this is h bar times the same thing. So this is virtual class. This is the same thing reduced. And this is this object here. What is the dimension? This dimension equals. So this guy has dimension. So the dimension of this guy is 1 less because we have less marked points. So this will be dimension x minus 1. This is for 1 fewer for marked point. And then you have plus 1. This is for reduced. So altogether, this 2-pointed, this correspondence has the same dimension of X. So you may not be impressed at this point, but this is half of a crucial dimension count. So once I do the second half, then maybe it'll be better. On the other hand, maybe let's write this correspondence CD. We can consider the map. So x is not a projective variety. It has plenty of functions on it. In fact, we'll get to that. So if I have a variety, then I can look at all possible functions on it. And if this is a finitely generated ring, then I can map X to the spectrum of that ring. I mean, just look at the image. Just give image of X by all possible functions. So in other words, there's a map to spec. I mean, in this case, it's abstractly show it's finitely generated. So, but let's so spectrum of global functions. So I'll write a fancy way each sections of the structure. Let's do that X naught. One can, I mean, this course one can consider abstractly, but the point is that for Grassmannian there's a great many global functions. And so this is, of course, an affine variety. And so if I have a affine algebraic variety, so in particular, any curve, any complete curve, any complete subscheme, any particular, any rational curve, will be collapsed by the map to the affine variety. And so, therefore, my scheme CD sits inside. This is a correspondence, but it's supported on pairs of points. So what's this product? This means pairs of points on X that go to the same point in this affinization. Right. So now this is a very general fact. So these are very general facts. We can verify them explicitly for Grassmannian, but this is very general fact. Very generally used in theory of Nakajima variety. Is that this variety like X is such that this map is in fact, there's so many functions, it is in fact birational. But more importantly, that this thing here is at most the fibers of this. So the fibers of this so small that this thing is at most. So when is this variety big? Is that like if I have my X all going to one point, then X cross X. X cross X over that point will be just have dimension twice X. But this, in fact, this guy here is at most Lagrangian, at most half dimension, at most half dimensional. And its components of half dimensions are Lagrangian. i.e., the dimension of X cross X is not is dimension of X. And so we see we have a cycle of this dimension supported on a variety of this dimension. And so conclusion CD is a Q-linear combination. it's Q because when we this moduli of curves, it's really an orbit. Means there's some finite automorphisms, and so one really has this virtual class is only defined. I mean, in this case, in the case it happens with respect to Z linear combination, but in general there could be finite automorphisms, and then you will have the virtual class is only defined with rational coefficients. And so you see, we got seems like we got a really a lot of mileage from, because in general we were we were looking for some unspecified cycle, and in fact the cycle we already know, it's some multiplicity that we need to compute. And in fact there's only one component that really contributes, so we'll get to that. But so this also, I can maybe say that this is also, the argument is completely will not work in K-theory. In K-theory, when some K-theory class is supported on the right, there's not so much you can say about it. But in cohomology, this is very sharp. It's true in K-theory it's also true there will be some K-theory class that sits in here, but this is much harder to compute with distinct cases. But anyway, so now maybe we have to look a little the 5 minutes remaining, but maybe I'll have to look a little bit on what this variety is. So how does one think about what is the cotangent bundle to Grassmannian? Well, maybe I'll explain this part, and this will be the end. So Grassmannian is, after all, it's the quotient you take matrices of. You can take like a basis of your vector space. So this means take n by k matrices of rank k, and you mod out by JLK. So if I take, so maybe we'll call this matrix, A. It's a matrix that, think of this as a map from CK to Cn, which is like, the image of this is your subspace, and what you mod out are reparameterization in the domain. And so if I have a quotient, then what is the cotangent bundle to the quotient? So I have a quotient, there's some pre-quotient, and I have some point, and I have a G orbit. So that's some point, maybe call it A, and then I have like the whole orbit of the point. So then if I, when I look at the cotangent space, like a cotangent space, of course it's a cotangent vector, maybe call it B. But for this to be, it should be really a function on, so like the tangent space to the quotient is the tangent space to the pre-quotient modulo the terms you get from the action of the group. So maybe modulo, so this tangent weight here is the space of like psi A, where psi sits in the Lie algebra of G. And so since I want B to be a function of the quotient, means B has to be paired trivially with any such vector. So this is a map, in other words, T star to like A mod G. This is, you look at sets of pairs. You look at B and B and T star A, satisfying the condition that B pairs 0 with psi A. This you mod out by G. So But this is the moment map. I mean, if you think of this as a function of psi, this is the moment map. Moment map in general is defined. Moment map, so it means mu of the pair AB. Paired with psi. Moment map in general is defined for general symplectic manifold is defined somehow, but if it's your general symplectic manifold is a cotangent to something on which the group acts, all you do is the following: you have a point, a covector, and an element in Lie algebra. Well, you just act by the vector field, and you pair it with the covector. That's the moment map. And concretely here, that means there is a. Now we're going to get into the basics of Nakajima variety. So this means the B is a map that goes the opposite way. So B is a matrix. Looks like this. And then psi is really a matrix there, and it's really the pairing. This pairing here is just really the trace of a B xi divided. And so this means this has to be for any xi, and so that means to be the case that BA has to be 0. This is for any xi. This means the moment map has to be 0. So then in other words, T star Grassmannian is the quotient of pairs A and B, rank A equals to K, BA equals 0. And so now this affinization map over there So what's a global function on the quotient? It's invariant polynomial. Okay? So if I look at if I have by first fundamental theorem, what are the invariant? So if I have, representation, another representation, and I have map by first fundamental theorem of invariant theory, all invariant polynomials are obtained by contracting indices. That's all there is. And the contraction indices concretely means that if I take the composition B times A, this is invariant. So if I pair AB, then this going to A times B, this is an invariant. And all matrix coefficients of this are invariant, and this is a complete set. So what's the image of this map? Well, maybe we'll call this matrix, I don't know, D. So what do we conclude? D is a matrix of size n. D square is 0 because if I multiply this, so since or put differently, the eigenvalues of B and A, the non-zero eigenvalues of B times A and A times B are the same, and so therefore all eigenvalues of Z is 0. But in fact, it's square 0 because if I write AB, and I get BA, and so this square is 0, and the rank of D. Well, it's not. It's bounded by both, since it has to. It's at most the minimum. Okay. And so once I know this D, then how do I reconstruct A and B? Well, what are my so since A since A is injective, B is reconstructed from D uniquely. If I know A, then I know B. A has no curve. A is injective. But well, what are my choices for A? Well, I have my image of my matrix D, and I have the kernel of my matrix D, and A has to be somewhere between the image of it. And so in particular, if it is the case that this is at most k, for example, let's say k is less than n over less or equal than over 2, and let's say this is k dimensional. If this is really k dimensional, there's only one choice for A. And so this is I'm trying to say the generical, this map is birational. The generic fiber is just one point, because the image of A has to contain the image of D. If this is k dimensional, then this has to be that. Since A is injective, then B I know it uniquely from B. Anyway, there's some homework problem on this stuff. You can since I'm over time right now. So our maybe I'll summarize where we are. We got to the point that there is some. This variety x over x with x over its affinization called the Steinberg variety, or maybe called the Steinberg variety. It's not exactly the classical Steinberg variety, but maybe called such. Has very interesting components. In fact, we realize that our cycle is just a Q-linear combination of some of these components. And in fact, it's only one component is relevant. We'll see somehow. It's better on over time in the 2-hour lecture. And only one component there is relevant. And so it's only very, in the end, there's some number, just like one number we need to compute. And that's this is where the bell rings to be continued tomorrow. Same time, right? Same 2-4.